Chalmers University of Technology is a leading technical university in Sweden and is leading the effort to develop a Swedish quantum computer using superconducting circuits. These circuits need to be cooled down to a very low temperature, so the quantum chips are placed in a dilution refrigerator type of cryostat. And these cryostats are quite cramped, not a lot of space, so wires in them take up a lot of the space. And this is fine when you only have a few qubits, but becomes prohibitive when you want to add more and more qubits. Also, every line going from room temperature into the cold inside of the cryostat is an opening for noise and heat to leak in. And this is something we want to avoid. And also, not to mention, superconducting cables are rather expensive. And these are obstacles that we encounter trying to scale up to the very large number of qubits that is needed to perform useful quantum algorithms and calculations. One approach to solving this problem and reducing the number of cables going into the cryostat is to do time domain multiplexing, where you have a single line or just a few going into the cryostat into a switch that can route the signal between multiple different qubits. In order not to heat the cryostat, this switch needs to be superconducting as well. Chalmers has a long history of over 40 years of research in superconducting materials and components, and we have state-of-the-art laboratories to measure these components. And nowadays we do many measurements involving qubits. For these reasons, our role in this project is to benchmark the superconducting switch in a practical use case with a qubit chip. We looked at a couple of alternatives to the superconducting switch, but respectively they had a few downsides. For example, not being superconducting and thus heating the fridge, or being controlled by a magnetic field which can disturb the very sensitive qubits. This project also gave rise to new and very relevant questions, like how does the overhead from time multiplexing, switching back and forth, affect the results when you run actual quantum algorithms? And how can you optimize the switch configuration to achieve the best possible performance? These are interesting questions we started to look into in collaboration with our theory colleagues at the department.